This lesson is the second in a series of lessons on summary statistics. If you didn't already see part 1 on central tendency, you might want to see that lesson first. In this lesson, we're going to take a look at different ways of showing variation, or how data is spread out within a data set. This is often a useful way to look at a collection of data in order to determine whether the measurements or values are clustered closely together or spread out very far. One simple measure of data variation is called the range of a data set. The range is indicated by the capital letter R and is found by subtracting the lowest value in a data set from the highest. In this example, the highest value is 44 and the lowest value is 3. So the range is calculated to be 41. This number doesn't tell us much on its own, but if this range is compared to the range of another data set, we would be able to see which data set is spread out more or less. This is nice because it's easy to calculate, but range only takes into account the highest and lowest values in a set, and doesn't tell us much about how the other data points are distributed. For this reason, the range is highly influenced by outliers. So if there's one abnormally high or low value in a data set, the range might communicate a degree of variation that doesn't represent the overall collection of data very well. A more reliable measure of variation is called the standard deviation of a data set. This is a little more difficult to calculate, but can provide us with a very descriptive picture of how data is spread out within a set. The larger the standard deviation, the wider the spread of data. Again, this is only informative when the standard deviation of one data set is compared with another to give context to the measurement. The formula for calculating standard deviation can be found on page 1 of your PLTW formula sheet. It's important to note that there are two formulas given for standard deviation on the formula sheet. The first is for finding the population standard deviation. This formula is used when data has been measured for the entire population being studied. For example, if data was collected about the height of every student in class, the formula for population standard deviation would be used since the height was measured for everyone in the population. The other formula is for finding sample standard deviation, which is used when data is only available for a small sample of a larger population. For example, if heights were measured for every student in a class, and that sample of data was used to represent a larger population, such as all the students in the school. Mathematically, the formulas are nearly identical. The biggest difference is in the denominator of the sample standard deviation formula. Instead of using the actual size of the population, the formula uses the size of the population minus 1, which takes into account the uncertainty of applying sample statistics to a larger population, for which measurements were not taken. In general, when asked to find the standard deviation, you should use the population formula unless a problem specifically states that the data represents only a sample of a larger population. Since the population standard deviation is the most commonly used, let's break down this formula to see how it works. On the left side of the equation, population standard deviation is represented by the lowercase Greek letter sigma. On the right side of the equation, x sub I indicates each individual data value in the set. Mu represents the mean of the data set, as we saw in part 1 of this lesson on central tendency. The capital letter N in the denominator represents the size of the population. Again, for this formula, we're working under the assumption that we have data for the entire population in question. This complicated formula becomes a bit easier to understand when it's broken down into steps. First, calculate the mean, or mu. Next, subtract the mean from each data value in your set, and then square each result. Then, sum all the squared differences that you found during step 2. Add them up. Next, divide the summed value by the size of the population, n. And finally, calculate the square root of the result. Remember, don't round before your final answer. And when you find the standard deviation, round the reported value to one more decimal place than the original data was given. Since we're given a finite data set and are not told otherwise, we assume we have a data value for each member of the entire population, and we use the population standard deviation formula. First, find the mean of the data set. Note that if we were asked for the mean, we would report the mean to be 47.6. However, we'll use the unrounded value stored in the calculator when calculating standard deviation, because we're not quite done yet. Step 2. Find the difference between the mean and each data value and square each difference. Note that these values are calculated using the unrounded mean, but they're rounded to 2 decimal places since it's unwieldy to report a large number of decimal places. It's preferable to save each unrounded squared difference in your calculator so that we can add them together. Step 3. Sum all the squared differences. In this case, we'll find the sum to be 5,024.5455. Note that the sum shown is calculated using the unrounded values, and so the total is slightly different than the total you would get when adding the rounded numbers. If you use the rounded squared differences, the sum is nearly the same, 5,024.53. Step 4. Divide the sum by the number of data values, which for this problem is 11. Remember to use the unrounded result from the previous step. Step 5. Take the square root of the division. Remember to use the unrounded result from the previous step. Report the standard deviation to one more digit than the original data. Since the original data in this problem was given in whole numbers, the answer here is reported to 1 decimal place more at 21.4. Again, this number on its own doesn't say much about the data set, but when compared with the standard deviation of other data sets, we can see which set has the higher or lower standard deviation. That is, we can see which data set is more or less spread out. Standard deviation can be calculated fairly easily using spreadsheet programs like Microsoft Excel or Google Sheets. To see how, check out my video Statistical Data Analysis in Excel. Part 3 of this lesson will talk about distribution and show several different graphical methods for communicating summary statistics visually. To find out more about standard deviation and what it can tell us about a data set, check out my video lesson on the empirical rule. Thanks for watching.